Good afternoon, my name is Tony Peters. I'm going to be presenting the synthetic aperture radar testing and verification using UAVs. Here's some of our learning objectives. We're going to define what a UAS is and its relation to synthetic aperture radar. We're going to define what the actual background and fundamentals are of SAR, what's the perceived need of this system or this innovation, this research project in and of itself, what are the research hypotheses and the question, what's really the problem we're trying to evaluate, the methodology, what's our plan to actually get this question answered. Going to talk about some of the data and the interpretation of the data, the research findings, and summary and recommendations. So what is an unmanned aerial system or aerospace system? It's usually comprised of the UAV or a series of UAVs. The ground station or aerospace data facility, you could have several of those in your architecture. You could also have remote ground stations for a lot of smaller UAS, SUAS-based systems, whether it's somebody just driving around on a Jeep with a laptop and a controller, or something a little bit more sophisticated, something that's just set up at a FOB, potentially a forward operating base. And then the UAS operators themselves. The UAS relationship with SAR, so we're trying to figure out, hey, what's the relationship historically between these unmanned vehicles and use of SAR? Well, it's pretty prolific and outfitted on many terrestrial and space-based UAS for geospatial and other types of missions at the unclass level that we won't talk about. But the Galileo constellation is just one of these examples. And SAR has even been used to improve the navigation abilities on smaller or medium or even larger UAS should their inertial navigation system, INS, basically that's co-located with their global positioning system, fail. And that's been shown to work with pretty good results. So what is synthetic aperture radar? So what's the background? So it's based off of radar technology, but it's bounded by the antenna size. So SAR comes into play because the antenna size was the limiting condition. So in 1951, we found out ways to precisely analyze that return frequency of a system by synthetically generating an antenna. So it makes it think that the antenna is larger than it really is, bottom line. So the use of SAR is ideal for those persistent overhead remote sensing operations, and it's ideal because it can penetrate cloud cover, which is a pretty large game changer for geospatial intelligence users. And then we'll cover some of the design and test of some SAR equipment. But there is a long-standing history of UAS using it for terrestrial systems prior to be used on a UAS system, on a UAV basically. But we're trying to bridge that gap between UAS for terrestrial and space sensors. So here's some fundamentals. So we have the spacecraft motion. We have a velocity vector v going along the planet's surface or scanning along the planet's surface. The image swath is something we'll talk about as we talk about some of the beam modes and the different types of beams that you can use, because obviously it's not just going to be the one type of beam in one band that we're going to be talking about, but it is an active sensor that emits energy in the microwave band, and it's going to measure that returned energy to generate an image. So here's just some SAR beams and types, again, as platform moves along in orbit. So here's some of the swath widths just to give you a gauge. So the standard beams, it'll just go and scan along this surface topography. For example, in this research project, we're going to be looking at it as trying to identify vessels or objects in a maritime environment. So you can have it a little bit wider, a little bit more fine. So you can see here that the swath width and the coverage is limited depending on this type of beam and the type of band, because it can generate exactly how wide this thing is. And then a wide scan SAR, excuse me. And these different beams with the same sensor are unique to a mission that it's trying to do, or a different phase in the orbit. It might try to collect something a little bit more widespread here, but have tasking to have a little bit more fine resolution there on the flip side. So what's the perceived need? So we don't need to, but there is a need for developing more cost-effective solutions for all types of sensors, specifically for military applications and users. And what we're trying to do is minimize the technical risk for space programs by creating a unique test opportunity. And this is known as risk reduction testing, so we'll talk about that a little bit more. So what's the hypothesis? What's the question? What's the problem? Okay, so we're trying to say that the null is that UAS is a cost-efficient test platform for SAR sensors that we can use on future spacecraft. Conversely, that the alternative hypothesis is it's not. What's the question is that UAVs, can they serve as a viable test platform for space SAR? And we want to talk about the costs, the time demands, and that risk reduction testing that was mentioned earlier. We want to minimize technical risk for programs looking to use new SAR technology. So what's the approach and plan? So we want to gather all the relevant data pertaining to SAR, the technology, the background. I want to talk about the numbers associated, that quantitative data showing how reliable is it in XLC band for determining a vessel of interest in a maritime environment that's with a pretty high sea state. So we want to look at that, the qualitative data in terms of the current and future SAR technology, and then the applications. What are these other SAR sensors used for? I think that's very important for the research project. And then we'll review some of the current high-flying UAS and the balloon technology. Which type of UAS would probably be best for this? What types of test environments? What other sensors have been tested as a means of RRT? That's valuable. And then finally, looking at what does the pub say? That's a big question we ask the Navy. What does the publication say? Where is that written? The MIL Standard 1540 Delta and Echo series is just an example of the standard that you have to follow for you being like a military program, for example, developing a space-based sensor or a spacecraft. You have to abide by some of the conditions that are written in there to meet some of the harsh environments of space. AIA, the American Institute of Aeronautics and Astronautics, excuse me, that's also another one for individual component testing. So we want to review those test procedures for space programs, and then we can tailor our research project and what information is going to be relevant moving forward. So looking at our initial test criteria based off of data, and we put together some assumptions. I keep saying we, excuse me. I mean to say I. I'm used to working in a large engineering group with people, so excuse me. So we got some assumptions listed here, and we'll go right into it as far as how I put the data together and how I analyzed it. So the main objective is to determine the viability of the SAR equipment being tested on an unmanned aerial system, or a UAV, to be used for spacecraft later on. It's intended to be operated at different altitudes, and LEO is low Earth orbit is an orbit that I chose to use because it's more favorable for satellite imagery based off the quick revisit times and this relatively short period here and close proximity to the Earth's surface, as opposed to like a highly elliptical Earth orbit, HEO. Characterized for the research project about 90-minute periods and 300 nautical mile distance essentially from the Earth, and an inclination of about 63.4 degrees. So I didn't really choose something that was more so polar orbit. I dug this up from some other commercial programs, such as the Galileo constellation, that use that inclination as opposed to some other ones like those more polar, closer to 90. So that was one assumption. TRL, so technology readiness levels, was another assumption. So how mature is the system? So this is the definition of it up here, but really what it boils down to is we want to try to take something from a TRL 4 status, which is basically like a prototype in a controlled environment in a laboratory, to a 5, which is like a working prototype in a controlled environment, again, or a laboratory, to something like a 6. So essentially, this ties into risk reduction testing. So you want to know you want to know the valuable information, test data, to show that this sensor is going to work, or build confidence that it will work when you get further into the integration or engineering life cycle for a space program. Say, all right, this technology is not really mature. It's got a low TRL level, and it's going to cost money. This is where it really boils down to. It's going to cost money to test this equipment and integrate it. So you want to try to save money by doing all the testing earlier on in the program, as opposed to way later on than experiencing all these other problems. So it's important to mention technology readiness levels in terms of technological maturity and growth of a system. So what's the actual UAV I plan on using? So for this research project specifically, I chose the MQ-4C Triton UAS. It has a very wide history with both conventional SAR and inverted synthetic aperture radar systems, and testing this new sensor or new technology where the MFAS is. And it's high altitude testing up to 60,000 feet, and it has a high gross weight capable takeoff, and that's something that's very ideal for the system that we tend on using. And Triton's obviously based off of Global Hawk, for those of you who don't know, and I'm sure most of you are very familiar, if not intimately familiar, with Global Hawk. And so this was my selection here. And thanks to some recommendations from other students in the class, I chose to look at a manned flight vehicle as well. So as a secondary means of validation, because there's aircraft are flying all the time. And traditional manned aircraft before have tested synthetic aperture radars before, up to 800 pounds sensor payloads. So the Boeing 707 JSTARS seems like a really good idea. At least it did to me at the time, but I also looked into the U.S. Navy, the new Poseidon P-8. It's already got a very wide breadth of knowledge as far as tactical exposure and experience and using these SAR sensors. So I figured, well, okay, these people are already, the crew's already proficient, so it may worth, like my last bullet states here, maybe worth considering the use of this large multi-crew aircraft with high altitude capabilities. For testing these SAR sensors. So moving on to the costs. Okay, so like I said before, really want to try to burn down costs. So I wanted to try to narrow it down. All right, so how viable is it, manned versus unmanned aerial vehicles? So what this statement is essentially saying is that it is more cost efficient to use a UAV for testing new equipment. Whether this statement is based off of smaller UAS, large, medium, it does seem to tie into all of those, and really tying with the theme of cost, you want to try to reduce that as much as possible. So maintenance costs, things of that nature, operational costs. I mean, you could just go out and compare MQ-1 operating cost versus, let's say, an F-16 cost. That's just a very I don't want to oversimplify the example that I'm meaning to use here, but as an assumption early on in this research project, it's pertinent to address costs. So we're going to keep going forward with the UAS solution from now. Again, trying to figure out how we're going to use this in an environment and mission. That's something that's also good to kind of knock out right now early on. So we want to standardize the way it's tested. We're going to standardize the region to promote some of those consistent test solutions and conditions. And then I ended up coming up with this SAR sensor will be the target recognition and will be used for target recognition in maritime environment. So what this figure is basically doing is just highlighting some of the test variables associated. Again, platform velocity as it's moving across, chirp pulse will be discussed later. This XY focal point be kind of like that fine or wide angle resolution or that coverage that we were talking about before. And then this H sub SAR, the altitude that is being used for the vehicle to gather that SAR solution. So initially I made some claims saying that the H sub SAR is going to be a direct function of spatial resolution, and that the delta in altitude between a terrestrial and space-based sensor is going to be the main constraint when testing terrestrial SAR to be used in space. So I've also identified some of the variables that are important to mention in maritime environments, such as sea state, the sea level winds. It's pretty rocky out there, so you're going to get those resultant white caps. That's going to adversely affect your SAR solution. And then the scattering from the sea surface is also another one. This is the SAR geometry of which I'm basing a lot of my test variables and limitations on for space and for terrestrial environments. So here we're talking about my establishing my test criteria, the technical limitations. So altitude right off the bat, we're going to assume for a MQ-4C Triton just under 10 nautical miles and 300 nautical miles for the low end of the LEO spectrum in that orbit. C, again, that chirp pulse will be the velocity of the microwave, which is a function of many other things, band being one of them. And RT and R are going to represent that's slant range distance, and then we talked about the target XY at the ground coordinate system origin, so that'll be something to talk about. And then this also played a huge part. The platform velocity vector is a test variable. It limited my UAS selection to something like Global Hawk or Triton, excuse me, in that balloons would be really good as far as altitude considerations and stability, but not good due to their inability to move about the x-axis, and it kind of limits their coverage. So looking at the technical limitations also helped me go backwards and say, all right, well, I can eliminate these type of UAS as potential sponsors of a new SAR sensor. So now let's go into the research findings and how I interpreted the data. So again, that delta in altitude is about 290 nautical miles. We want to try to determine how impactful this difference is to the spatial resolution. And a lot of other programs had used pretty robust computer modeling efforts specifically for a maritime solution. So this empirical geophysical model function, the GMF, was a big one used to estimate wind speeds, tilt modulation, and things of that nature for essentially looking at that really dynamic SAR spatial resolution type picture, and obviously is very impactful in how I'm going to make my findings here. So we can use models such as this to standardize the methods of how I'm actually going to get that SAR imagery collected, and also for a sensor independent of altitude. So again, we talked about that XY coordinate function. What's the focal point? Where are we actually looking? Where are we directing our pulse and our energy towards, whether it be a terrestrial or space platform? So it's the point where the altitude could be directly linked to that spatial resolution based off the type of band used. So X, L, and C as an example, some common bands anyway. And that velocity vector V is another constraint. The differences in V, obviously there's a massive difference between a spacecraft traveling in LEO versus Global Hawk or Triton or a P8 traversing at 60,000 feet. So using modeling will be good for that. So going back to the altitude, you want to talk about terrestrial versus space. So atmosphere 1 is as close to that 14.7 psia, 101.325 kilopascals at 1 atmosphere versus atmosphere 0, which is where you really want to test it. And it's mentioned in TRL maturity of a sensor or a program or something that's going from terrestrial to space based off of the 5 to 6 level. It has to be relevant environment. So something like that is definitely worth mentioning. So the changes in V, that velocity vector between the two platforms at different altitudes being measured, we want to look at that resultant magnitude of change between that in the modeling effort. And then the earlier that we can test and validate this technology, the better. And it will save program dollars later on as the spacecraft matures and grows in size and gets more and more components built onto it. So really what's something we can use as an early stage testing and validation? So for the maritime environment, automatic information system, the AIS, is something that's used for tracking ships. And we can couple that with a SAR sensor to validate the vessel or return, saying, hey, this is actually, 1, there's something there, and 2, that is the right vessel that you're looking for. So we can add this capability with a UAS, which again, I've flown with AIS integrated into our aircraft, and I flew a helicopter, so if that doesn't tell you, these boxes are pretty small. So adding it on to the SAR sensor itself and the SAR boxes or components may really assist in validation of those radar returns. So this is just a basic flow chart of something that I picked up from a very relevant research project, in that it's coupling a SAR image and AIS data, pulling from a registration database, and it's trying to get a resultant assessment of what's actually going on. So it starts to break down into these 4 different types where, long story short, you want this. You want SAR and AIS to link up so that it can use AIS saying, yes, your SAR image, there is an actual solid return there, 1, and 2, it is the vessel of interest that you're looking for. Maybe it could be something that's correlated to an instance of missile launches or something like that, and saying, hey, we're looking for this this type of vessel in this box in this area of the world. That's a vessel of interest. So you can use AIS and SAR in early stage testing to validate that and then identify those results. So again, moving forward with the interpretation of data. So I made the claim saying that the altitude could be a direct impact or a function of spatial resolution. However, there's a lot more that plays into that. And according to this, high resolution capability is something that you get from SAR, but it is independent of flight altitude. So this research project is already starting to shift from, okay, something I thought was initially a constraint, but it's opening a little bit more than I could have bit off more than I could chew, essentially, because there are a lot more variables for an aircraft in LEO per se that present more significant issues than just the operating altitude, i.e. the method of scan, the interferometric techniques, the repeat pass, single pass, based off of the image that I showed you earlier. How are we actually trying to compress the signal or orthogonal coprime? These are just types. These are methods in which we project that energy onto the Earth's surface, and how that refracts or bounces off or is absorbed. Those are going to play into much larger effects to SAR effectiveness in terms of the spatial resolution scheme than just altitude. The specific band use and the synthetic antenna size, again, also have large impacts to that SAR performance. So I've identified that a lot of those things were performance factors or key performance factors that can't be validated in a terrestrial environment or are significantly limited to test in a terrestrial environment when trying to compare it to a space platform. But you could still use unmanned aerial systems as a function to reduce, as a risk reduction testing, as a RT. But doesn't account for some effects that we'll get to in a second. They could address some of the technical risks from going to a breadboard or to a prototype stage, so from 4 to 5 in a controlled environment. So you could save some money in that regard. And you can use that to save weight, minimize power consumption, and maximize the performance to using that smaller design. So going from breadboard to prototype, that type of information could be very, very useful. Okay, so in summary, unfortunately, UAVs do not currently serve as a viable test platform for space-based SAR. The Triton could provide a solid altitude-consistent platform for that long-range testing, but again, it's limited in terms of velocity vector v, which we'd have to use modeling efforts for. So it's we're kind of tied in terms of cost at that point, because we can use a computer modeling software to validate some of these things versus sending out multiple missions on an expensive P8 crew. Again, how that speed of travel V relates to swath width is important. We're also unable to account for those harsh environmental variables to the actual sensor and spacecraft and just the boxes themselves due to the thermal oscillations present in LEO. So LEO can range anywhere from -70 degrees C to anywhere upwards of 100 C. So you got a really oscillating thermal environment there. So radiation hardening and high photon density environments due to the South Atlantic anomaly, that's just one example of just these high energy protons or photons just hitting your spacecraft and presenting a lot of issues. And some of the ionospheric and atmospheric refractions are also unable to account for at that AM1 or atmosphere 1 type terrestrial UAS. Also determined that altitude has very little to no impact on that spatial resolution, as opposed to all these other variables that I just talked about. The high-flying balloons, again, they are a type of UAS. They might give research teams a semblance to EMI and some of those atmospheric effects for some of your boxes, which is very valuable. But it is limited in range coverage, as mentioned previously. So, in summation, the research does not support the use of UAS as a cost-efficient test platform, supporting the alternative hypothesis, and does not support the null. So what are the recommendations? What are we going to do from here? So some of the open work that I recommend is those sophisticated modeling and simulation efforts to determine or predict SAR performance as a function of band use. So chirp pulse, velocity, the platform velocity, and then the spatial resolution as more of a function of band and all those other factors that we talked about before, going all the way back to the geometry of SAR and how it works. And also, it's just really good to get analysis of the appropriate photon density and some of those thermal ranges by doing some thermal distortion testing based off of full sun, different beta angles, different portions of the orbit, things of that nature. It'd be really good to incorporate those into those modeling and simulation efforts. And modeling and simulation is also another very widespread proven method of early stage risk reduction testing for a number of programs. So there's no reason we shouldn't be using modeling and simulation in conjunction with a potential UAS solution going down the road. And like I said, to close out, all this open work will be valuable as a means for that early RRT. Some other things to think about would be, as new technology comes about, it's good to revisit this topic. So for ground testing, TVAC chambers, thermal vacuum chambers, photon excitation chambers, looking into how practical is it to use to increase TRL status based off of these new sensors that are coming out, and then the new sensors being tested in these new methods that are coming about. And then higher flying UAS or cheaper commercial space launch vehicles. Such as the SpaceX Falcon 9. The SpaceX Falcon 9 is the recoverable first stage rocket that you've heard about for launch vehicles. And 75%, up to 75%, of launches are due to the first stage. So if you're able to have something that's reusable, that could be another way to burn down risk and minimize cost for a program. And then in closing, as UAS technology emerges, it's recommended to continuously revisit those based off of the reduction of technical risk and increasing TRL status. With that, I open up the floor to any questions, and here's some of my references. So you could take a look at some of the peer-reviewed scholarly publications that I've used for this research project, and looking forward to any critiques. Thank you for your time.